Thanks for watching my video today. Let's try to prove this interesting integral. Then is the integral from 0 to infinity of e to the negative ax cos bx dx, which is equal to a upon a square plus b square, okay? Where a and b is not equal to 0, okay? I mean, if a is 0, b cannot be 0, and if b is 0, a cannot be 0, okay? So now I'm going to prove this in two ways, okay? Now the first one is just using integration by parts, okay? So let our integral to be I is equal to integral from 0 to infinity of e to the negative ax cos bx dx, okay? So now if you take, now let us take cos trigonometry to be first function and this is second function, okay? So the first function cos bx, integration of second function then is integration of e to the negative ax is e to the negative ax upon negative a, okay? From 0 to infinity minus integral from 0 to infinity. Now differentiation of first function, that is differentiation of cos bx is differentiation of cos is sine, okay? Sine bx negative sine bx, and then differentiation of bx is b again, into integration of second function then is e to the negative ax, which is e to the negative x upon negative a, okay? Here if you put infinity here, so e to the negative infinity is 0. If you put 0, so okay, right, for infinity in is 0, then is cancel. For 0 it will be negative times negative will be positive, right? So cos 0 is 1, e to the 0 then is e to the power 0 is just 1, that's why 1 over a is here, okay? Now this and this minus and minus become positive, and this negative it is here. Now b by a, b and a is constant, so b by a, right? Taking out the integral from 0 to infinity e to the negative ax sine bx dx, right? Now let us use again IBP for this part, so integration by parts, okay? Let's do once again. So our integral I is 1 over a minus b by a. Now first functions then is sine bx, integration of second function then is e to the negative x upon negative a, right? From 0 to infinity minus integral from 0 to infinity, differentiation of sine is cos, right? Cos bx, and differentiation of bx is b, and integration of e to the negative x is e to the negative x upon negative a dx, right? So if you put infinity here, this will be 0, I think, right? If you put 0, so sine 0 is 0, meaning this whole term will be 0, okay? So our integral I is 1 over a minus b by a. This whole term is 0, right? Negative and negative become positive, and b by a is taking out again, common, right? Constant. So integral from 0 to infinity e to the negative x cos bx dx. So the integral, this integral, if you see our original integral here, right? This is our beginning, so this integral is nothing but our what we are trying to prove, that, okay, right? So I call it I, right? So our integral I call it I, so therefore integral I is 1 over a, so this minus, right, minus b times b is b square, a times a is a square, times this integral is nothing but our original I, right? Therefore I, so this one coming out here, so it will be 1 plus b square by a square times I, which is equal to 1 over a. So here if you simplify this, a square plus b square by a square times I is equal to 1 over a, right? So you will get I is equal to 1 over a into a square by a square plus b square. So this 1a and here 1a will cancel, then you get a upon a square plus b square. Therefore our integral from 0 to infinity e to the negative ax cos bx dx is a upon a square plus b square. This is what we are trying to prove, right? Now here is our, this will be our second proof, okay? Using different method. Here the first one is we are using integration by parts 2 times, right? Now here I'm going to use the exponential Euler formula. Okay, we are going to use Euler formula. Okay, let's do the second proof. So this is the second proof. I is equal to integral from 0 to infinity e to the negative x cos bx dx. We know that from Euler identity, right, or Euler formula, e to the ix is cos x plus I sin x, right? This is a well-known identity and due to Euler. Okay, so integral I is integral from 0 to infinity e to the negative x cos bx dx is equal to this part. Cos part is nothing but this one, right? This is what we call the real part, and this sin x is nothing but the imaginary part. Why? This I is nothing but our imaginary number, right? So that's why we call this part is imaginary part, and this is the real part. So our cos here is cos, right? So there will be here is cos, so it will be our real part, right? Our real part of integral from 0 to infinity e to the negative x. In order to get bx, if you put x equal to bx, right, e to the ibx dx. Okay, now I is equal to the real part of integral from 0 to infinity. So these are both exponents, so it will be, let's combine them, e to the negative. I'm going to take negative common here. Negative a minus ib, right? A minus ib times x dx. So integration of e to the power integration of exponential will be e to the negative a minus ibx by negative a minus ib, right, from 0 to infinity. So I is equal to the real part of, if you put infinity, so e to the negative infinity is, we know it is 0, and minus become positive. Okay, the minus and this minus will become positive. If it is 0, so e to the 0 is just 1, right? E to the 0 is just 1. Okay, that's why 1 over a minus ib. Then you get real part of 1 over a minus ib, which is, this is the conjugate, right? If you take the conjugate of a minus ib, then you get a plus ib. The conjugate of a minus ib is a plus ib. Okay, so since I put it in here, so I'm going to put it in the numerator again. Now simplify here, real part of a plus ib upon here a into a minus b, a plus b, right? A square minus b square. So a square minus b square. B square is nothing but ib whole square, right? And I square b square. So we know that I square is not negative one, right? Negative b square, right? This negative, and on the formula it will be negative 1 will be negative there, so it will be positive a square plus b square. Therefore, if you take the real part, a is the real part, right? And this b is the imaginary part. That's why we take the real part a only. So which is a upon a square plus b square. Therefore, integral from 0 to infinity e to the negative x cos bx dx is a upon a square plus b square. That is what we are trying to prove here, right? And the good thing about this Euler identity is that if you can find out for cos, right, then we can easily find out for the sine also, right? Then meaning e to the negative integral from 0 to infinity e to the negative x sine bx dx is, if you take here the imaginary part, so then is b upon a square plus b square, right? So that's why if you for solving these types of question, if we use this Euler identity, we can get two result. Okay, we can get two result. So this is, there are other method to prove this integral also, but these two, I'm choosing these two. So this is how it is.